In today's lecture, we will see how the MRI signals fill the case space. We also see the fast scan techniques, such as gradient record per sequence, fast spin echo per sequence, and echo planar imaging. Now let's see first spin echo per sequence. The slice selection gradient is made up of two gradients with opposite slope size. So this is slice selection gradient, consists of opposite slope gradients. The position dependent phase in the slice is generated by the first positive slope gradient, this one. However, the spins are effaced by the second negative slope gradient, enabling the spin echo per sequence to begin with maximum longitudinal modulation. The second slice selection gradient to replace the spins. The phase and frequency encoding gradients are applied at the same time when the second gradient of the slice selection gradient is on. This one. There are two gradients in the frequency encoding gradient. This and this. The first gradient is used to dephase spins, so, whereas the second is used to rephase spins in order to detect the MR signals. So the second gradients rephase the spins, so it can detect MR signals. The area of the second gradient is twice that of the first gradient. The area of the second gradient is twice that of this first gradient. At the center of the second gradient, here, the echo signal is at its maximum. By changing the slope of the phase encoding gradients, the above process is repeated until the desired resolution is achieved. So you can change the slope of phase encoding gradient several times, 250 times, 56 times. Repeat the same procedure. Now consider the phase change in each spin echo per sequence process. The phase change of x direction, actually, theta x, for this direction, frequency encoding direction. The spins dephase according to the first frequency encoding gradient in the process A to B. So this first frequency encoding gradient dephase the spins. Okay? So phase is change for from A to B. After that, until the 180-degree pulse of the spin echo per sequence is applied, there is no phase change. So from B to C, we don't have any gradient, so phase does not change. And then the 180-degree pulse then reverses the phase from C to D. So this 180-degree pulse reverses the phase from C to D. Okay. There's no phase change in the process D to E since no gradient is used. So no gradient is here from D to E, so phase does not change. Okay. The echo signal appears at position E, at this position. At the moment, the second frequency encoding gradient is on, due to the second gradient of the frequency encoding gradient. The spins entirely rephase to generate the largest echo signal at the center of the frequency encoding gradient point F. At this moment, the echo signal has its maximum. So phase is 0, right? So we have the maximum value of the signal. Following the completion of one spin echo pulse sequence, the spins are rephased by the slide selection gradient. So we go back to here and repeat the process again, okay? Allowing the above process to begin again with the different slope of the phase encoding gradient. So we change the slope of the phase encoding gradient, and the same processes are repeated 256 times for the 256 pixel image. Now let's see how the MR signal field K-space. During the spin echo pulse sequence, the MR signal fills the K-space as seen in the figure. This figure describes how the gradient affects the K value, which location corresponds to the K value, and how the spin echo pulse sequence fills K-space. The Fourier transform of the K-space gives the MR signal. Once K-space is filled, then this K-space is fully transformed, and then we can get the MR image. Now let's see how the MR signal fills the K-space. The K value is 0 before the gradient is applied. This corresponds to horizon A, this point. The positive slope of the initial phase encoding gradient is largest. First, we try largest phase encoding gradient. Okay. And the initial frequency gradient is also positive. So it is positive, right? As a result of the processes A to B, the coordinates of the point B in the K-space are Kmax, Kx max, and Ky max at this point. The phase encoding gradient has its largest value, the largest slope. So y max, ky, y max, and the frequency encoding gradient is positive. So the position of ky is also its maximum position here, P. So A to B for this process A to B in K space, A is here and B is here. There is no gradient and consequently no phase change during B to C process, resulting in B and C being in the same position. So B and C, from B to C, there is no gradient. So B and C are in the same position. Now 180-degree pulse at C of the spinnaker pulse sequence, then reverse the phase. So 180-degree pulse is applied at this position C, and then phase is completely change their signs. So x maximum becomes minus kx maximum, ky maximum becomes minus ky maximum. So at this position D here. So as a result, coordinates are changed from C, kx maximum, ky maximum to point D, minus kx maximum, minus ky maximum in this process. Now the second gradient of the frequency encoding gradient is then applied at this position, at this point E. Then the echo signal begins to appear at the 180 pulse and peaks at the center of the second frequency encoding gradient, point F. So phase will become 0 at F, and we have the maximum signal, and then up to G the signal appears, disappears. At frequency signal disappears. Signal appears from point E and disappears at point C. So from E to G, signal is collected. So from E to G, K value will change in this direction. Therefore, one line in the K space is filled after processes are complete. So one line in the K space is filled. This one. Okay. The phase encoding gradient is then decreased slightly. So first we use the largest slope phase encoding gradient, and then we use the slightly different slope of the phase encoding gradient. So ky is changed, slightly changed here. Okay. So the ky is lowered. And the spinnaker pulse sequence continues to operate. Then slightly above the first line, another parallel line in K space is filled. So the same process here. Due to this 180-degree pulse, phase is reversed. So going here and E to G, one line of signal is filled. Okay. The K-space is completely filled with the parallel lines if the same process is repeated until the maximum positive slope is reached. Okay, this maximum negative slope. Okay, this maximum negative slope of phase encoding gradient. Then we did 256 times of this process was complete. Then K-space is complete filled with data, MRI signals. So we can have 256 signals. That means 256 lines are filled. So using this filled K-space, we do fully transform of these signals, and we can get the MR image. For the image of 256 by 256 pixels, 256 lines are used to fully fill the K-space. As a result, the spinal cord sequence used to generate an image ends up at point K x max, K y max, which entirely filled K-space. The signals in the K-space are then Fourier transformed to produce the MR image. In K-space, time interval between lines equals TR. Hence, the time necessary to produce an MR image is equal to the number of lines times TR. So we need 256 TR times to generate an MR image. So time interval between two lines is TR. So we have 256 lines. Lines means a signal. So we have 256 signals, and for each signal we need TR time. So to complete one image, we need 256 TR time. Now let's see the first scanning techniques. Gradient record for sequence, record just the GRE, and the first spin echo, FSE for sequence, and echo planar imaging. If the TR is long and more phase encoding processes are used, the imaging time increases. If the imaging time is too low, the patient will move and the MRI image quality will decline. First scanning techniques have been developed to solve this problem. Typical first scanning techniques include first spin echo, gradient echo, GRE, and EPI, echo planar imaging. In FSC, after the first 900 degree, 100 degree, 180 degree pulse sequence, the FSC employs repeated 180 degree pulses to obtain echo signals continuously. We will explain in details what in the FSC pulse sequence we use repeated 180 degree pulse after spin echo pulse sequence. On the other hand, in the GRE, the partial flip angle pulse is used instead of the 900 degree pulse. Once this pulse is employed, the longitudinal magnetization's recovery time is shortened, and so the imaging time is considerably reduced. However, there is a drawback in this case, which is reduction of signal intensity. The GRE is partially popular for 3D imaging. Particularly, the GRE is particularly popular for 3D imaging. The slide thickness in 3D imaging is generally thicker than in 2D imaging. Since there are more photons in thicker samples, the signal intensity is larger. The EPI uses a series of sinusoidal pulse sequences for the pulse encoding gradient. This sequence of pulses allow us to acquire a large number of echo signals at once, considerably reducing imaging time. However, for the faster interrupt of on and off for the field gradient, more capable hardware for the high performance gradient is required. Now first see the gradient decode pulse sequence, GRE pulse sequence. The 180 degree pulse is used in the spin echo pulse sequence to dephase the dephasing spins. On the other hand, the gradient echo signal is produced in the GRE pulse sequence by applying the dephasing and the rephasing gradients in order. So we use in GRE pulse sequence, we use dephasing pulse and rephasing pulse. So we use dephasing and rephasing gradient fields in order. Okay. The transverse magnetization rapidly decreases as the dephasing gradient field is applied to the nuclear spins in the image slice. Using this negative slope focus encoding gradient, the dephasing of nuclear spins occurs. If the rephasing gradient field is applied in the opposite direction of the dephasing gradient field, the nuclear spin become in phase, resulting in the gradient echo signal. So if you use a rephasing gradient signal, opposite direction of this first one, then the phases of spins become zero and gives the echo signal. In the spin echo pulse sequence, A 90-degree pulse transforms all longitudinal marginalization to transverse marginalization. However, in the GRE pulse sequence, a pulse with a less than 90-degree pulse angle converts some longitudinal marginalization to transverse marginalization. So in spin echo pulse sequence, we use the 90-degree pulse, so all longitudinal marginalization becomes the transverse marginalization. However, in the GRE pulse sequence, we use the partial angle pulse, so some of the longitudinal marginalization will become the transverse marginalization. The TR, time of repetition, in the GRE pulse sequence is a fraction of what is in the spin echo pulse sequence. The typical TR in the spin echo pulse sequence is about 16 milliseconds, while the typical TR in the GRE pulse sequence is only 15 milliseconds, generally 4 times less. Two gradient fields with opposite slopes make up the slice selection gradient, the same as in the spin echo pulse sequence. The first gradient defaces the nuclear spins in the slice, while the second gradient field refaces them, allowing the GRE pulse sequence to begin with all spins in phase. So using the opposite slope gradients, we can deface the all spins before starting the GRE pulse sequence. The phase and frequency encoding gradients are applied at the same time when the second field of the slice selection gradient is on. This is also the same as in the spin echo pulse sequence. So we are using phase encoding gradient and the frequency gradient at the same time of the second slice selection gradient. Next step is to apply the second frequency encoding gradient, this one. The nuclear spins are then defaced, producing the gradient echo signal. At the center of the second frequency encoding gradient, the signal has maximum. By varying the slope of the phase encoding gradient, 256 times, this process is repeated until 256 signals are produced for constructing the slice imaging. Now let's see the phase change in the GRE pulse sequence. Phase change means phase change in x direction, frequency encoding direction. The nuclear spins are defaced by the first negative frequency encoding gradient. The process from A to B, we use the negative largest phase encoding gradient first, and frequency encoding gradient is also negative. So here theta x means the this frequency encoding gradient, so A to B phases become negative. Since low gradient is employed in the process B to C, so phase does not change. There's no phase change. The nuclear spins are replaced by the second positive frequency encoding gradient, and at the center of this second gradient, the nuclear spin aligns. So phase will become 0 at point D. So replaced, resulting in the gradient echo signal. So at this center of this second frequency encoding gradient, the signal has its maximum, and at this point C, the echo signal appears, and after this point E, the echo signal disappears. So between C and E, we have echo signal. Now let's see how the MR image fills the K space in the GRE Fourier sequence. The K value is 0 before the gradient is applied, which corresponds to the origin A, starting point. The negative phase encoding gradient and also negative frequency encoding gradient. So first we use the negatively largest phase encoding gradient. So negatively largest slope of phase encoding gradient. The negative slope of the initial phase encoding gradient is largest. In addition, the frequency encoding gradient is negative at first. So first frequency encoding gradient is negative slope. As a result, the initial process A to B renders both Kx and Ky negative, resulting in K space coordinates of minus Kx maximum minus Ky maximum. So from A to B, moving here. So A to B. Okay. During B to C process, there's no gradient and thus no phase change, resulting in B and C being in the same position. So B, C are in the same position. During C to E process, and this process, a positive frequency encoding gradient is applied to obtain MR signal. As a result of positive gradient, the K values increase to Kx maximum. So Kx value is moving to Kx maximum. But since there's no phase encoding gradient is applied during this process, Ky remains constant. So in this way, in this direction, so one line is filled. So echo signal is obtained during the second frequency encoding gradient. This echo signal is largest in center D, here, and diminishes as it moves away from the center. Okay. The one line in the K space is filled after the process is complete. the phase encoding gradient is then increased slightly, and the GRE for sequence continues to operate. So we use the negatively largest slope at first, so this one at first, and next we increase phase encoding gradient slightly, this much, and repeat the process again. Then we can fill one more line. Okay. Then slightly above the initial line, another parallel line in the K-space is filled. So this one. The K-space is completely filled with the parallel lines if the same process is repeated until the maximum positive phase encoding slope is reached. So final process, the phase encoding gradient is largest. So largest phase encoding slope. Okay. Then we have the signal. In this case, the signal fills this line. Okay. So 256 lines filled K-space. To completely fill the K-space, 256 lines are usually employed. As a result, the GRE per sequence for an MR image finishes when the K-space is completely filled at position, this position. The signals in the K-space are Fourier transformed to produce the MR image. Total scan time for an image and GRE per sequence. In the GRE per sequence, the total scan time for an MR image is given as TR, time of repetition, and NY, number of process of the phase encoding gradients, and number of excitation is a pulse. So just one pulse and one pulse. Number of slices. For this 3D imaging, we can use many slices at a time. So at this time, we have to multiply the number of slices here. And Y is the number of phase encoding steps, gradients, necessary to produce an MR image. If TR is 30 milliseconds, one excitation, one alpha pulse, and NY 256 are used, then for one MR image, we need 7.68 seconds. The partial flip angle of less than 90 degrees is employed in the GRE per sequence. Thus, only a fraction of the longitudinal modulation is converted to transverse modulation by the pulse. As a result, for a small angle pulse, T1 relaxation time does not provide for tissue contrast. Okay. The photon density weighted image is therefore obtained for small angle pulses. However, if large angle pulses are used, the T1 weighted image can be obtained with a not too small TR. Okay. If TR is very small, TR for the TRE pulse sequence is typically a few tenths of milliseconds, Residual transverse modulation affects the following signal for a small angle pulse. As a result, in this situation, T2 star weighted image is obtained. If TR is long, a few hundred milliseconds, T1 is more heavily weighted and image. Okay? In the GRE pulse sequence, T effect is comparable to that in the spin echo pulse sequence. As T decreases, okay, then T2 star effect diminishes, but T1 or proton density effect is weighted. So we can get several different weighted image for the what kind of TR we used. So we used the small angle pulses. Then we can have the proton density weighted image, and if you use not too small TR, then we can get the T1 weighted image. And if you use very short TR, then T2 star weighted image can be obtained. So the image style is different according to what TR time is used. Now next, see the fast spin echo pulse sequence. During TR, the dead time, right? The FSC pulse sequence uses a series of 180 pulses to detect a series of echo signals. So this is spin echo pulse sequence. And after that, we use a series of 180-degree pulses to detect the MRI signals. So from here to here is TR. If we do not anything, then this time is just the dead time. Right? Using this dead time, we apply a series of 180-degree pulses. Then we can get a series of MR signals. In the same time span as TR, a set of 90-degree and 100-degree pulse in a spin echo pulse sequence is applied, and an MR image is detected. So if we do not do anything during TR, we can have just one MR signal after this spin echo pulse sequence. So just one MR signal is detected. However, in the FSE pulse sequence, the phase encoding gradient with a different slope is applied before each 80-degree pulse. We are applying phase encoding gradient before 180-degree pulse. So we change the phase each step. Okay. So in the FSC pulse sequence, a phase encoding gradient with a different slope is applied before each 180-degree pulse. So this is negative register and increasing, and 0 at here, and positive and increasing. So for each 180 degree pulse, we have to change first the phase a little bit. Okay. As a result, each echo signal relates to a single K line. Okay. In the figure, 180 degree pulse applied during a TR. So during TR, we applied 1, 2, 3, 4, 5, 6, 8, 7, 8. Okay. So 180 degree pulse applied during TR. Is that right? 1, 2, 3, 4, 5, 6, 7. The 7, right? Including this, okay. So result in filling of 8 lines in the K space at once. So including this, we have 180 degree pulse. So for each 180 degree pulse, we can have a MRI signal. Okay, so we can get 8 MRI signals at once. That means during TR, we can get 8 MRI signals. So this corresponds to fill the 8 lines in the K space. Thus, obtaining an MR image takes only 32 TR. So 32 times at each step, we can get 8 MR signal. So if we do the 32 process, we can get 256 signals, which can fill the K space for an MR image. So obtaining an MR image takes only 32 TR, implying that time required for an image using FCE per sequence, as illustrated in figure, is just 1 over 8 that required for the spinal cord per sequence. So we can save the time 1/8 of the time for the spinal cord per sequence. An MR signal is obtained through an 180 degree pulse in the spinal cord per sequence. This means that a signal, just one signal, can be obtained during TR, okay? And a line in the K space can be filled. So if NY lines are required to fill K space for an MR image, it will take NY times TR times NI by times TR times to produce the image. So for an MR image with TR equal 10,000 millisecond and NY equal to 256, for example, then totally we need 256 seconds for an image. This is for the spinal cord sequence. But in the first spinal cord sequence, we use the 180 degree pulse. Then the time needed for one MR image, we need 256 divided by 8 seconds. So 32 seconds. Okay. Right. So if you use the spinal per sequence, we need 256 seconds for obtaining one MR image. However, in the fast spin echo per sequence, or in this case, we use 8 180-degree pulse, then we can get 8 spin echo signals during TR. So that means that we need just 32 seconds for obtaining one image. The time needed for an image is just 1/8 of the required for the spinal cord pulse sequence. Okay. In the FSC pulse sequence, the effective TE is the time interval between 90-degree pulse and the zero phase encoding gradient. So this position. So from here to here is effective TE. TE effective. Okay. So phase encoding gradient is changing every time before 180 degrees pulse is applied. The interval between subsequent 180 degree pulses in the figure is 20 milliseconds. So this between these two points is 20 milliseconds. Is also 20 milliseconds. And the fifth phase encoding gradient is 0. So at this position, phase encoding, no phase encoding gradient. At this position, 0 phase encoding gradient. Here minus 20, minus 40. Oh no. This is a large slope and a little negatively larger slope of phase encoding gradient. So this slope is slightly increasing, and here 0, no phase encoding gradient, and the phase encoding slope is increasing slightly. Okay, so from negatively increasing and passing to 0 point and increasing. Okay, this way. So fifth phase encoding gradient is 0, this position. As a result, the FSC pulse sequence in the figure has effective T of 100 milliseconds. So each interval is 20 milliseconds, and at this point, so 100 milliseconds. So this FSC pulse sequence, the effective T is 100 milliseconds. The FSC pulse sequence in the figure should be repeated 32 times for the NY equal to 56 to create an MR image. Okay. So for each this process, 32 times process, we have to set this the same position. Okay. So 0 phase encoding position should be the same position. Okay. To meet the requirement, the fifth phase encoding sequence in each step is set to 0. So we have to maintain the phase encoding equals 0 position should be the same. So for obtaining one MR image, we have to do this process 32 times, because one process we can have 8 MR signals, so we have to repeat 32 times, then we can get 256 MR images to fill the case space. So this is 32 times process. We have to set the position of the 0 phase encoding in position should be fixed here. As a result, the K-space center is filled by 32 echo signals obtained from 32 FEC per sequences fifth encoding gradient. So at this position, actually here, right? That's 0. Before 180 degree pulse, we applied the phase encoding gradient. So at this position, we have 0 phase encoding gradient. So we have the largest echo signal here, 100 milliseconds. So in this position, the signal intensity is decreasing. From here also decreasing. So effective T position, we have largest echo signal. The T2 weighted image is obtained for long TR and long T in spinal pulse sequence. We already discussed this one. T effective acts as TE in the FSE for sequence. Hence, in the case of T effective 100 millisecond long T, so we have T2 weighted image. The proton density weighted image is obtained for long TR and the short T in the spinal pulse sequence. So if you use T effective 20 millisecond, will be suitable for this in the FSC for sequence. The image scan time will be TR times TY divided by ETL. So ETL is the number of 180 degree pulse. So 64 seconds. When we use TR at 2000 milliseconds, T go 100 milliseconds. So we use 180 degree pulse and NY at 156. Then we can get the image scan time at 64 seconds.